What are your questions? If you have one, you can unmute yourself and just go ahead and ask away. There's few enough people in here. If there get to be a lot more people in here, we'll put you on the participant listing and you raise your hand. And I look in the window to see if you have your hand raised.
I have
So,
a question.
Go ahead, Charlotte.
Number 9 on the homework.
Okay. I don't know what that is, so let me take a look at it, all right?
Okay.
More than likely, it's one that I just wrote from the back of the book. I'll be honest with you.
Okay.
So let me see if I can find it in our course shell. Right now, I'm opening up the shell. And I'm going to module 1, homework. Yeah, that's one where I did, or did I write out the solution? I think I did write out the solution, but this is one where it probably helps to see how it's handled by a person in real time. So what I'm going to do here is I'm going to share my screen so that everyone can see the problem. Where is my, okay, share screen. Okay, so there is the problem in front of you with number 9. And while you're doing that, I'll try and find out what problem it is in the back of the book or in that particular chapter. If you want to look in your book for this problem, it's on page number 52, and it's problem number 30. And the reason I'm telling you that is because in just a moment, you won't be able to see the problem because I'm going to show you how I solve this problem. I'm going to take a few quick notes and note that I need to convert the data to 1 over amount. And to 1 over velocity. And I need a table of those results. Got to plot it where I put 1 over the amount on the X and 1 over velocity on the Y, and get a straight line. Get the slope intercept form. And use the internet. Oh, wait, do not worry about significant figures. Use the internet to graph the same. So that means you have to go online and find some sort of graphing program. Of course, if you have a TI 83 and you know how to use it, you could use your TI 83. But I don't know how to get a screenshot of your TI 83. You're just going to have to take a photo of it and add it to your results. And then how did you do? Okay. So let me do this. I'm going to back out of this and I'm going to go to homework solutions. Because some of this I won't have to do, I can just show it to you. And actually, I think I can pull this up. Open recent homework 1 solutions. Okay. So I'm going to go to a new share screen. And there it is. And I'll make this full screen here. Let's see, where's the view? Zoom. We'll make it 200%. Okay, so I'm going to scroll to number 9. Okay, so there's the information. Does everyone see the information from number 9 on your screen top? Okay, great. So this is the information as copied from the problem. And when I scroll down, you're going to see the values that I get for each of these. Now, for the 1 over amount of H2O2, does everyone see the 0.510 to begin with? Let's go back to the other table, and you see that it is 1.96. So if you take your calculator, handy dandy calculator, this is the one I like. It's like $10 at Target, solar powered, never needs batteries. So if I take 1.96 and then take the inverse of that, I get 0.510. So that's the origin of the 0.510. Is everyone okay with that? Now, let's take a look at something that's a little more difficult. You see this 4.5 times 10 to the minus 5? I'm going to do a different share screen with you. Okay, so now you're looking at my calculator. And I'm trying to zoom out so you can see the buttons that I'm about to push. And I'm going to go back to that one screen. You'll still see my calculator, but I'll see that screen. And I'm going to look at the actual number. So 4.75 times 10 to the minus 5. I want to get the inverse of that. So can everyone see my calculator? So 4.75. And for the 10 to the minus 5, I push the second button and this EE button, and you get this little symbol E. That E means times 10 to the. So if that means times 10 to the, I'm going to put -5 in there. So what's nice about the EE button is that it treats this thing like it has parentheses around it. So I can hit this x to the minus 1 and enter, and I get 210,000 or 21,052. So 21,052, I see I have a rounding error here. It should be 2.11 times 10 to the 4th. Now I'm going to change my share screen back to the table. So do you see this 2.10? Should read 2.11. I rounded incorrectly, but that is the origin of that value. So rather than show you how to calculate each one of these values, you now should understand how these values were calculated. Are there any questions there?
No.
Okay, go ahead.
Oh, no, no question.
Okay, now I'm going to pull out some graph paper here, if I can find it. Ah, I know where it is. So here is my graph paper. I'm going to change the share yet again. So here's my graph paper. Let me zoom out so that you can see the extent of it. I'm going to take a piece of graph paper out. And looking at this graph paper, I can see that there's about 5, 10, 15, 20, 25, maybe about 30 squares this way, and 5, 10, 15, 20, 25, 30, 35, and about 40 this way. Okay, so I'm going to plot that data on this graph. Try and get rid of that shadow there. Okay, so you're going to continue seeing my graph paper. I'm going to switch screens so that I can actually see the data. You won't see what I'm seeing. You'll just continue to see this graph paper. Hang on a second here. Okay, so I asked you to graph 1 over the amount on the x-axis and 1 over the velocity on the y-axis. Now, the reason my graph paper is oriented like this, which I call, most people call landscape, I'm orienting it this way simply because you can see it better that way than if I switch it this way. So by default, that means that this is going to be down here, my x-axis, and this is going to be the y. So when you start to write a graph, and I've got to switch my screen real quick so I can see that you can see the graph paper. Okay, good. Why is this so hard for me to do? Okay, so we're going to put 1 over the amount here. So that's, if you will, the unit for this one, or actually this is the heading of that table. And let me see, how is amount measured? They don't give us a measurement, so we just write 1 over amount. And this side is going to be 1 over reaction velocity. And the units here are seconds per amount. Now, for the amount of H2O2, it goes anywhere from 0.5 to a maximum of 6, correct? So to use this whole axis here, I want to have 0 over here and 6 over here. And if I have about 40 squares and I divide 6 into 40, 6 goes into 40 about 7 times, right? So if I say that every 7 squares is 1, I'll get to 6 when I get over here. But 7 is an awkward number to use when you're trying to divide up things evenly. So I'm going to go with 5, and I'm going to label this here as 0, this as 1, this is 2, 3, 4, 5, 6, 7. And you can see I am using most of my x-axis, which is what you want to do. Now, for the y-axis, we're plotting 1 over reaction velocity. And to do this, it's really a pain to figure out how to space things when I'm using 2.10 times 10 to the 4th. So I'm going to change this top unit, and I'm going to say this is times 10 to the 4th. So that means the numbers here, I can use 2.10, 2.48, and so forth. So I want to go from here to here, and I want this to be 17. Now, if I have about 30 squares here, I don't know if I'm going to be able to get away with saying each square is 2. So let's find out to make sure how many squares I do have. 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28. I don't even have 30. I've got 28 squares. So 28 divided by 17 is about 1.5. So I can make each square 1.5. And that means that this would be 3. But if you have from here to here being 3, it's an awkward amount of space to divide. But if I make it into a 4, then I know that this is 1, this is 2, this is 3, this is 4. It's very easy to do. Are you with me there? So I'm going to put 4 there. This would be 8, 12, 16, 20, 24. Oops, I did that wrong. 4, 12. This shouldn't be 16. I'm going to cross that off. That should be plus 8. So this should be 20. This should be 28. And then 28 plus 8 is 34. And then this is going to be 42. So you can see if I'm going to go up to oh wait, that didn't work out right, did it? I should have made this 2, 4, 6, 8, 10, 12. Okay, I was
think
thinking
the screen
backwards.
is frozen, Tony.
What's that?
I think your screen is frozen, like your screen share. Okay.
Is it still frozen?
No.
Can you see my arm moving around?
Yeah.
You know what? Probably because I was looking at the other screen for too long, it froze.
Okay.
But at any rate, I'm going to cross all of this stuff out. And I'm going to put the numbers on the inside: 2, 4, 6, 8, 10, 12, 14, 16, and then 18. And so I'm using quite a bit of this axis, and it prevents me from having to make this like a 1.5 or making this a 2 or something like that. It's just neater to do. It's easier to do. So I'm going to switch back to looking at my other screen. This screen may freeze again, and if it does, you need to let me know, okay?
Okay.
Because apparently we can fix it pretty easily. But I also need to look at the numbers. Okay, so the first number is going to be 0.510, which is about here, and 2.10, which is about here. So there's my first point. And then 0.763, this is a 0.6, 0.8. So 0.763 is going to be right around here. And 2.48 is going to be, if this is 2 and this is 3, 2.48 is about halfway. So it'll be about right here. And then 1.0 and 2.85. And then 1.5 and 3.97. So here's 1.5. And 3.97 for all practical purposes is 4. And then we have 3.0, which is over here. And we have around 7. And then finally, we have 2 more. We have 6. No, wait, I already did the 3.0. Now we have 6.3, which is right here. And we have 17.1. So this is 14, 15, 16, 17, 17. And so that's about right there. So there's our graph.
I think it's frozen.
Perfect timing. How about now? We good?
Yeah.
Can you see my hand? Okay, so we have all the points plotted. And now what we want to do is we want to draw a line for these points. And what you tend to do is something like this. Do you see how essentially none of the points are on the line? But I'm trying to draw the line as close to the points as I can. And you know, you might have done something like this instead. You know, it really doesn't matter as long as you try and get the line close to the points. If these were the points, this is something you don't do. You don't draw a curved line. So this is a no-no. Are you with me there? Okay, so now I want to get this equation of this line. To get the equation of the line, I'm going to use this line right here. I need to get 2 points on the line. So I can't use this because it's not on the line. Now to get points on the line, I'm going to use this guy right here. I'm going to put a circle around it. The reason I'm going to use that guy is because that point, that part of the line is on a line that's vertical and a line that is horizontal. So that point there, if this is correct, is 0.6 and 2. So that's one of the points I'm going to use to get my equation. And this point right here, do you see how that is also right at a crosshairs? So that one is 5.2 and 14. Okay, now what I'm going to show you next, I normally do not do on the graph itself, but I'm going to do that here. So to get the slope, which we often represent by the symbol m, we do the change in y over the change in x. I do not like to use the phrase rise over run. And the reason for that is when people use rise over run, they look at how many squares there are, and that's the run. And they look at how many squares there are, and that's the rise. And that works as long as each square is the same height as it is wide. Ours are not. So a more sophisticated method and a better method is to do change in y over change in x. So we know these second values are the y values, right? So this is 14 minus 2 over 5.2 minus 0.6. And I can do this in my head, sort of. 14 minus 2 is 12. 5.2 minus 0.6 is what, 4.8? So 12 divided by 4.8 should be more than 2, but less than 3. So I'm going to plug these numbers into my calculator and see what I get. 12 divided by, I'm going to go ahead and do 5.2 minus 0.6, and I get 2.6, which is between 2 and 3. And I think in the assignment I wrote down, just use 2 zig figs. Maybe I said 3, but I think I said 2. Okay, so there's the slope. So that means that y is equal to 2.6x plus b. How do we get b? Well, it's simple. I'm going to use b is equal to y minus 2.6x. So I've just taken this equation, I've rearranged it so I have b on one side and everything else on the other side. And then to figure out b, I'm going to plug in this y, 14, minus 2.6, and this x, 5.2. So I can see that this number is probably going to be close to 0 because 2.6 times 5.2 is going to be more than 10, but probably less than 15. Maybe pretty close to 14. So I get 0.48. And that's the this value here. Okay, so now I have y is 2.6 x plus 0.48. Now, the reality is if we take a look at these numbers, is this. All of these y values are times 10 to the 4, correct? So this 14 is really times 10 to the 4. This 2 is times 10 to the 4. So what does it do to this value? It makes it times 10 to the 4. Likewise, down here, this is really times 10 to the 4. And the slope really should be times 10 to the 4. So this should be times 10 to the 4. So my real equation looks like this. And there you go. That's the equation. Now, the other part was to figure out a particular number by plugging in x and finding out what y is, or vice versa, plugging in y and figuring out what x is. So is this enough of this particular problem, Charlotte?
Yeah.
Okay, so this is something we expect you to be able to do in chemistry, is to graph out data and figure out the equation of the line, and then use that equation of the line. Let's actually look at the question again. So this may freeze. So here's what I did with a computer. You can see it looks a little bit different because this is more of a square graph than a wide one. And you can see that the equation I got here was 2.4 plus 1, whereas the equation I got today was 2.6 plus 0.48, which I would argue are pretty close together when we're just drawing lines in. Okay, and the internet gets a value of, when I plot these on the internet, I get 2.6x plus 0.24, which is even closer to what I got today. And oh, it doesn't ask us to plug in any values, just to compare them. So on the internet, I get a value of 2.59x plus 0.25. And now I'm going to go back to this screen. So this is what I got on the internet. And when I compare these two equations, 2.6 compared to 2.59, really close. The first time I did it in the answer key, I have a 2.4 here, but they're still pretty darn close. And in the answer key, I think I have 1.0 here. And on the internet, they have like 0.25, pretty darn close. So the idea here is you're supposed to understand that what the computer is doing, what the calculator is doing, is simply what you would do. The thing that made this one a little tougher is to do the 1 over the value, then plot them. So 1 over the value means exactly that. Take the value, divide it into 1.
Mm-hmm.
All right. Okay. Other questions? Okay, there being none.
I have more.
Oh, go ahead then.
I was just being nice, letting someone else chime in. I've been working on the back of the chapter questions.
Like page 24 or page 50?
50.
Okay, so some of the harder ones. Good.
So number 5 on page 50.
Okay, let me find that. So you're working on the ones that where they have answers in the back of the book.
I'm doing even and odd.
You know, if it were me, I would start off on the ones where there's answers in the back of the book. That way I would get more immediate feedback. Because guess what? I'm not going to email you at midnight. Not going to happen. I'm awake, but I'm not going to email you. I may see your email even and ignore it. Okay. Here's number 5. What I'm going to do here is I'm going to zoom in so that you can, well, so that you can read it, because you may not have your book at hand, or you have one of those digital books, and I don't know how well that works when you're trying to look at a Zoom screen and look at your digital book. So let's just take a moment and read number 5. Okay, does everyone have the understanding here of what we're about to do? We're going to change 42.195 kilometers to meters and also to miles. So there are 2 problems here. I have to zoom out, otherwise what I write is going to look like really big letters. So I'm going to write down 5, convert 42.195 kilometers to meters and to miles. Now I'm going to show you 2 ways to do A. Both ways are appropriate, but one way uses the conversion factor method. The other way uses the definition of kilometer. So this is one way of converting it. And the reason this works is because K is simply a placeholder for 1,000, which is the same as 10 to the third. So this method here is called substitution. I am substituting a number for K, because really it's the other way around. K is a substitution for a number.
Yeah.
Now, I'm going to show you another way to do this. We know that 1 kilometer is equal to 1 kilometer, correct?
Yeah.
If you're going to argue with me, I'm going to have to kick you out of the room here because you're crazy. Okay, now we know that K is 10 to the third, right? I just told you that. So that means 1 kilometer is 1,000 meters. So I substituted one of the Ks, but not both. I don't have to substitute both. Now I'm going to take this, and what I'm going to do is I'm going to get 2 conversion factors out of it. A conversion factor is a ratio of numbers and values. So these are the 2 conversion factors. In the first one, I have kilometer on top, and I have 1 times 10 to the third on the bottom. In the second one, I have 1 times 10 to the third on top, and I have kilometer in the bottom. Now, what is the size of 1 times 10 to the third compared to meters, that is, compared to 1 kilometer? They're exactly the same size. So what is this equal to if I have something on top that is exactly the same size as something on the bottom?
1.
It's equal to 1. And this is also equal to 1. Okay, so what that means is I can multiply this against anything I want, And I'm using the identity law, which says if I multiply by 1, I don't change it. So I'm going to take the 42.195 kilometers, and I'm going to multiply by 1 times 10 to the 3 meters over 1 kilometer. And the reason I chose this one is because if I have a kilometer in the numerator, because we all know that a number like this can be written as over 1, but we just don't bother doing it. When I have a kilometer in the numerator and another kilometer in the denominator, they cancel. So here, when I tidy this up, I get 42.195 times 10 to the 3rd meters, which is the same answer I got by substitution. So these are the 2 ways of doing it. And here, by memorizing that K means 10 to the 3rd, I can get that conversion very easily. The conversions you should memorize are mega is 10 to the 6. Kilo is 10 to the 3rd. Deci is 10 to the minus 1. Centi is 10 to the minus 2. Milli is 10 to the minus 3. Micro, which is the Greek letter mu, is 10 to the minus 6. Nano is 10 to the minus 9. Pico is 10 to the minus 12. You should memorize those prefixes.
So when I did my conversion factor, I got it wrong, but I need to know why, because I basically got the same answer, but was off on my decimal points.
So what do you mean by off on, can you actually read your answer to me?
I got 0.04219 meters.
Okay.
For the first conversion.
So what you did is you did 10 to the minus 3 here.
I didn't use that at all. My conversion factor was 1 meter over 1,000 kilometers.
Okay, so I want you to think, hold your arms a meter apart. Okay, now hold your arms 1,000 kilometers apart.
Okay, I think I know.
So shouldn't it be the other way around? Shouldn't it be that 1,000 meters are 1 kilometer?
Yeah, okay.
That's why you're off by a millionfold, is because you did this backwards.
Okay.
So this is the way to, when you're trying to get that amount between a meter and a kilometer, Charlotte, this is the way I start. And when I start this way, I know it's right. And then I substitute one of the prefixes with the real number it represents. And if I write this out without scientific notation, and I look at that, I think, that seems like it could be right. And to double check, I write it the other way. And I look at that and I think, that doesn't seem right. Because I know my car says kilometers per hour. I don't know why it would be saying meters per hour. I mean, it doesn't make sense, right? Because meters are small compared to kilometers. So you want to double check your conversions. Now, you used 1 meter over 1,000 kilometers, right?
Yes.
I'm going to show you how you can check this to see if it's right. Okay, Charlotte?
Okay.
So if you use this, you're saying that 1 meter is equal to 1,000 kilometers. Now, sometimes we don't understand what's going on here well enough to see that, no, that's just ridiculous. So here, what I'm going to do is I'm going to substitute the number for K, and that's 10 to the 3rd. So our question here is, does 1 meter equal 1,000 times 10 to the 3rd meters?
No.
So that means this is wrong. So you can always do that with your conversions that are like this. take the top, equal it to the bottom, get rid of the prefixes and put numbers in there. And if we have something like this, it ends up looking like this. And we know that is just another way of writing that. And I'm going to show you one more. So is this one correct? Let's find out. What's a K equal to?
1,000.
10 to the third, right?
Yeah.
What's 10 to the third times 10 to the minus third?
1,
We add exponents. So what's -3 and +3?
0,
Now, what is 10 to the 0 power?
0,
1.
Okay.
Any number to the 0 power is 1. So does it work out okay at the bottom? So what does that mean about this?
That it's equal.
That it's gold. It works. Okay. All right. So there's the second part to A, which is take this 42.195 kilometers and turn it into miles. Now, I don't happen to know the conversion between kilometers and miles. In addition, I want my conversions to allow me to keep 5 significant figures. So what that means is I want my conversion to be exact if I can and not rounded off. So what I'm going to do is I'm going to take my 42.195 kilometers, convert that to meters because that conversion between kilometers and meters is exact. I'm going to convert meters to centimeters because that conversion is exact. Centimeters to inches because this is a metric to English conversion that is exact. And then I'm going to go to feet, and then I'm going to go to miles. So I'm going to write 1, 2, 3, 4, 5. For number 1, I have 1 kilometer is 1 times 10 to the third meters. So you can see I kind of skipped the part where I put 1 kilometer equals 1 kilometer. But when you're learning this method, you don't want to skip that because you're not good enough yet. Number 2, 1 centimeter is equal to 1 centimeter. So what do I do with one of the C's?
Replace it.
Replace it. So I'm going to write 1 centimeter is 1 times 10 to the minus 2 meters. Number 3, this is one you should memorize. That's exact. That's defined.
Okay.
Number 4, I think we all know this one. 12 inches is equal to 1 foot, right? Whereas you don't know this one. .946 liters is equal to 1 quart. You don't know that one, right? So, but on this one here, let me ask you, which is larger, a liter or a quart? What's larger, a liter or a quart?
Quart.
Quart. No, it's a liter. And I'll show you why. Take a look over here. Which is larger, the inch or the foot? Larger.
Neither.
Yeah, they're the same.
What's larger, 1 inch or 1 foot?
Oh, 1 foot.
1 foot. Notice that the bigger number goes with the smaller unit, right? Bigger number, smaller unit. Oh, actually, you know what? I screwed up. Charlotte, the way I wrote it, you were right. It should be 0.946. No, I wrote it right. I doubted myself. Bigger number with the smaller unit. So which number is bigger, 1 or 0.946?
1.
1. So the quart is the smaller unit. So next time you go into a bar, which will probably be in about a year when they open up, and they say it's the same price for a liter or a quart, what do you want? You ask for the liter because you get a little bit more. Fair enough?
Sure.
Okay, what's number 5? This is one that many people don't know, but it is exact. And don't feel bad if you don't know it because it's not a big deal. We all know it's around 5,000, but we never know quite what it is. It's 5,280. So I'm going to start off with 42.195 kilometers. And for number 1, I don't need to write the conversion factors. There's another way to use these. I can simply say, I want to cancel kilometer. So I'm going to put 1 kilometer on the bottom. And I'm going to put 1 times 10 to the third on top. That is what I call, and other people call, dimensional analysis. Some people call it unit conversion. So I'm trying to cancel units that I don't like and introduce units that I do like. So that's number 1. For number 2, how am I going to use this? It looks to me like I want to get rid of the meter, so I'm going to put 1 times 10 to the minus 2 on the bottom. And the meter there, and 1 centimeter on top. So for number 3, I'm going to start crossing these out. It looks like I want to get rid of centimeter. So which of these do I put on the bottom? 2.54 centimeters. And then, which am I going to put on the bottom? 12 inches. And then which am I going to put on the bottom? 5,280 feet. And we're finally left with miles. So how do you put this into a calculator and not lose a whole lot of time? Here's what I do. I take all of the numbers in the numerator and I multiply them together. Then I take all of the numbers in the denominator and divide by them. So this is exactly what I do. I don't know if you can see my calculator. I'll try and tilt it so you can see it better. So I'm going to start off with 42.195. That's this number. And I'm going to multiply by 1 times 10 to the third. So let me zoom in on this a little bit. So times 1 second EE3. That's 1 times 10 to the third. And then I have times 1 times 1 times 1 times 1 times 1. I'm not going to put those in because I know it will not affect the answer. Now I'm going to put divided by 1. Whoops, sorry about that. So I have divided by 1 second EE negative 2. And this is where people make a mistake using this method. They go, okay, we're doing all the bottom ones, so I'm going to take that and multiply that times 2.54. No, you divide it by 2.54. Because you have to imagine what your calculator is doing is it's doing all of the operations until it gets to the 2.54. And when you look at the problem we have here, we're dividing by 2.54. So this will take your answer and divide by 2.54, which is what you want. Divided by 12, divided by 5,280. And if we think about the answer here, you might know that there's about 1.5 kilometers to a mile. 1.5 kilometers to a mile, roughly. So that means 42 kilometers should come out to about 30 miles. So if we've done this right, our answer should come around 30, not 300, not 0.3. And we get 26.2. So the answer is 26.21. And which of these numbers do I write down? I write down the first 5. And because the 8 is next to a 7, the 8 rounds up to a 9. And the reason we want 5 is because this has 5 significant figures. This is infinite, this is infinite, this is infinite, this is infinite, this is infinite. And when you'll multiply and divide numbers together, oh, you can't see what I just did. This has 5 zig figs. This has infinite, 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 infinite. When you multiply numbers together, you keep as many significant figures as the number with the fewest. And I would argue that 5 is smaller than infinity. What's bigger than infinity? Infinity plus 1. What's bigger than infinity plus 1? Infinity squared. What's bigger than infinity squared? Infinity to the infinitieth power. What's the biggest load of baloney you've heard today? The last minute of conversation. All right. So that's part A. Let's look at part B. Oh, that was part B. I separated into an A and B. All right, so if we had used the conversion between kilometers and miles from the book, we would have ended up with probably 3 or 4 significant figures because that conversion factor is not exact. It's not perfect. Okay, good. What's next? We still have 20 minutes. Charlotte's being nice because no one else is speaking up.
Yeah.
Go ahead, Charlotte.
Number 7, which is essentially more conversion, but I'm just getting hung up when it's the units squared or cubed.
Right. So let's take a look at number 7. I'm going to give you a chance to read it. And what I'm going to do for number 7 is I'm going to make a drawing. A lot of people say they're visual learners, but then they don't learn visually. So let's learn visually, shall we? So there's my postage stamp. Oh, you can't see that because I zoomed in. So here's my visual aid. And I don't know if you know this, but back in the day, the postage stamp had these weird edges. So that's what that is. We can even make it look like Tony's Facebook profile. So this is the Tony postage stamp. Are you with me? So we need to know that area is equal to length times the width. So if we need centimeters, square centimeters is what they say. That means centimeters to the second power. And meters, square meters, which is meters to the second power. We'll call this A and we'll call this B. For A, all we have to do, I'm going to use the symbol A for area. 2.5 centimeters times 2.5 centimeters. Oh, 2.1. Now I'm going to rearrange this so that we have 2.5 times 2.1 times centimeter. Because it turns out 2.5 centimeters really is 2.5 times centimeter. That's what it really is. And here I've just used one of the laws of math that says A times B is the same as B times A. So I can rearrange the order. So now when I do 2.5 times 2.1, I know that the answer should be bigger than 4 or bigger than 5, but by not much, right?
Mm-hmm.
So let's see what we get. 2.5 times 2.1, and I get 5.25. How many significant figures are in 2.5?
2.
2. How many in 2.1?
2.
2. How many significant figures are we allowed?
2.
Oh.
2. Now my calculator says 5.25, so I'm going to make that 5.3.
Okay.
Okay, now what's a centimeter times a centimeter? It's a centimeter squared. And there's your answer. Now for B, I'm going to show you a number of different ways to do it, but I'm going to show you the way that I think is the most efficient. So for B, here's my postage stamp, 2.5 centimeters, 2.1 centimeters. And I want the area in meters squared. So what I'm going to do is I'm going to take my 2.5 centimeters and say that's 2.5 times 10 to the minus 2 meters. And my 2.1 centimeters is 2.1 times 10 to the minus 2 meters. I'm going to substitute. So now I have the area is 2.5 times 10 to the minus 2 meters times 2.1 times 10 to the minus 2 meters. And I'm not going to do all the rearranging that I did before, but you're going to get an answer that says 5.3 times 10 to the minus 4 meters squared. And there's your answer. That's one way to do it. So we'll call this I. Here's another way to do it. 2.5 centimeters times 1 centimeter, 1 times 10 to the minus 2 meters is 2.5 times 10 to the minus 2 meters. And if you don't like this, you can always write 0.025 meters. Same thing. Some people don't like significant figures, but you need to get used to it in chemistry because we're working with either really big numbers when we're talking about how many atoms, or we're talking about really small numbers when we're talking about how wide an atom is. Okay, so you'd also do this with 2.1 centimeters and find out that that's equal to 0.021 meters. And we would find this answer to be 0.00. I'm just going to do it on my calculator. It's going to be really small. 0.53 meters squared. These numbers are identical.
I have a question.
Yeah,
Why not just convert the 5.3 centimeters squared using a conversion factor to a meter square answer?
we can do that. And that was going to be number 3.
Okay, because, okay, that's
So
what I'm
we
most
could
comfortable
take
with.
5 point, where's my first answer? We can take 5.3 centimeters squared and convert that to meters squared.
Yeah.
Now, over here, we know that 1 centimeter is 1 centimeter, right?
Yeah.
And I'm going to do something different. Most of us were taught the metric system in middle school. And your teacher pulled out a meter stick and they said, this is a meter stick. There are 100 centimeters in it. So we know that there's 100 centimeters in 1 meter. Some of us remember that from middle school. So if I use this, what do I put on the bottom so I can cancel out my centimeter?
Centimeters squared.
Well, this doesn't say centimeter squared.
No,
So let me ask you this. Is this correct?
maybe.
Here's a way to figure it out. Let's call that 1 meter and let's call that 1 meter, right? How many centimeters are there?
100.
100. How many centimeters are here?
100.
100. So if we say 1 meter times 1 meter is 1 meter squared, shouldn't we also say 100 centimeters times 100 centimeters is 10,000 centimeters squared? The answer is absolutely. Because here, if we look just at this, this says 1 meter squared is 100 centimeters squared. You see that right there? That's 100 centimeters squared. Because each one is a square centimeter. There's 100 of them. That's 100 square centimeters. Is this little slab equal to this big square? No. So this is wrong. So what you've done here, Charlotte, and this is a very common mistake, and I'm glad you made it now rather than on an exam, is if we have A times B is equal to C times D, are we allowed to say AB squared is equal to CD squared?
No.
Are we allowed to square only the B and only the D and make it okay? No. Are we allowed to square the whole side and the whole side and say it's okay?
Yeah.
Yeah. So here, if I square the whole side and square the whole side, I end up getting 10,000 centimeters squared is 1 meter squared.
Mhm.
Okay. So here's how I avoid it down here. I don't even deal with that. I'm like, I don't want to hear it. So here's what I do. I know this is gold. I know that's gold. I'm not going to square it. I'm not going to do anything to it. I'm going to use it just like it is. So if I use this way, do I cancel both of these centimeters?
No, that's why I was confused.
Now, I am multiplying by 1 because the number on top is equal to the number on the bottom, correct?
Yeah.
Can I multiply by 1 again?
Yeah.
So I'm going to use it twice.
Okay.
And that way, I don't have to worry about all of this gumbo up here. And you would get 5.3 times 10 to the minus 4 meters squared. Meter times meter, meter squared. Capiche? That's not a COVID cough, is it?
No.
Here, put your forehead against the screen. I'm going to get my little laser thermometer and see if you're running a temp. Okay. What would you do if it were a volume and it were centimeters cubed and you wanted to get meters cubed? What would you do differently?
Use the 1 meter equals 100 centimeters 3 times.
Correct.
Okay.
Okay, so this is how I deal with problems like that. Number 3 is my favorite method. I don't really like a 1. I don't like 2. I like 3 the best.
Yeah.
Okay, what's next? We still have 7 minutes. Terrence, any questions?
None prepared. No.
Well, you know what? It doesn't matter that you don't have any prepared. I'm glad to know you're here.
I've got number 10.
Okay, let me, the screen may freeze, but I will come back and unfreeze it. Or
And I
we'll
got
always try
hung up
to.
on the cubed units again. So I don't know if you want to do the same thing.
The aluminum package containing 75 feet squared of aluminum weighs approximately 12 ounces.
Wait, what are you looking at
Number 10?
in the back of the book?
Oh, I was looking 10 on the homework.
Chapter, I mean, page 50.
Okay, sorry.
Oh, number 10 on the homework is good too, but
Misunderstanding on my part. Some soft drinks are sold in bottles with a volume of 1.5 liters. What is this in milliliters? So here I'm going to say 1 milliliter is 1 milliliter. 1 milliliter is 1 times 10 to the minus 3 liters. 1.5 liters times 1 times 10 to the minus 3 liters. Why did I put this on the bottom?
to cancel.
To cancel. So
I
what goes on top?
have a question.
Yes.
Just so you're using scientific notation. Would it be okay to just do 0.001
Yeah,
liters?
it
Okay.
would be, but you know, suppose they asked you to convert this to nanoliters. What are you going to do?
Okay. That's a lot of zeros.
In my case, this is what I would do.
Okay.
So I don't need to worry about decimals when I use exponents. That's what's nice about exponents. I don't have to know how many zeros do I put in front. The thing that always bothered me is there's only 2 zeros in 0.003. I always hated that. You see
Why?
that?
Yeah.
There's 2 zeros, but it's 10 to the minus 3. 3.
Yeah.
I want there to be 3 zeros. So I always hated the idea that, well, you got to consider that the 1 is also over to the right of the decimal. It's not how many zeros there are, it's how many numbers you have to the right of the decimal. Blah, blah, blah. I hate it. So I just go with scientific notation. And there are very simple rules for scientific notation. 10 to the A times 10 to the B is equal to 10 to the A plus B. If B is -1, then and A is 5, it's 5 plus a -1. 1 over 10 to the A is equal to 10 to the minus a, which means that 10 to the a is equal to 1 over 10 to the minus a. For this one, I say if you cross the line, you change the sign. And the one that people always forget. Ten to the 0 is 1. Because really what this number means is
You're not timesing it by
10 to
anything.
the 0 actually means 1 times 0 tens. 10 to the 1 means 1 times 110. 10 squared means 1 times 10 times 10. And that's the way these are interpreted. And 10 to the minus 1 means 1 divided by 10. 10 to the minus 2 means 1 divided by 10 times 10. Tammy Matsumoto showed me that. Because I always asked her, why is 10 to the 0 1? It doesn't make any sense. She goes, oh, it's 1 times 0 tens. Like, oh, okay. I'm a math idiot. So this is the way I would do it. Now, Charlotte, you did ask, would it be okay? And the answer is yes, it would be okay. Okay?
Okay.
All right. Okay, how about in cubic centimeters? Let me get this answer.
Well,
For cubic centimeters, you should learn this.
isn't it the same?
They're the same.
Okay.
So on your first test, I would expect to see this if I asked you a question like this. You don't get to say, oh, they're the same. You show the conversion. Okay, how would you convert this to decimeters?
That's where I got stuck.
Now, this is what I would do. This is a meter stick. It's divided into 10 equal portions. Each portion is a decimeter. Each decimeter is split into 10 equal portions, and that's a centimeter. So how many centimeters are in 1 decimeter?
10.
Right, so 10 centimeters is 1 decimeter. And what I'm going to do here is I'm going to write 1.5 times 10 to the third centimeters cubed. And I'm going to use this guy. What am I going to put on the bottom?
Wait. Where are you getting 1.5 from?
That's what we had to begin with.
Oh,
This was
okay.
the answer to how many centimeters cubed it was.
So you're just writing it in scientific notation
Yeah.
instead of 1500. Okay.
So what am I going to do here?
You put centimeters on bottom.
Will that get rid of all 3 of these centimeters?
No.
So what do I do again?
Do it 2 more times.
Oh, did you see how Charlotte avoided my next question was, and then what do we do again? Do you know why she avoided that question? Because she has a kid. And that kid probably has asked her, and now what, mommy? And now what, mommy? And we get 1.5 decimeters cubed. And this is kind of interesting because if I circle these 2 numbers, 1.5 liters and 1.5 decimeters cubed, how big is a decimeter cubed?
What?
How big is a decimeter cubed?
Not
It's a
very big.
liter. It's a
Okay.
liter. So if you have a liter, that's 1 decimeter cubed of liquid. which means 10 centimeters by 10 centimeters by 10 centimeters. In this case, times 1.5. Okay, we've gone 2 minutes past the time. Now, in this morning session, we did a lot of stuff from pages 24, which is also end of the chapter problem. This chapter is split into 2 parts. There's a number of problems at the end of the first part, which is around page 24. There's a number of problems at the end of the second part, which is around page 50. The page 24 problems are the easier ones, but you want to be prepared to do those. If you want, though, you can watch this morning's session where we spent a great deal of time doing the even number problems from that area. But as always, priority goes to the people who have questions in these Zoom sessions. So I like that because usually a lot of people like to attend. They don't know what to ask. And if someone is asking, it's very helpful to see that other people have similar issues. Okay. All right. So at the end of every session, I tell everybody to turn on their microphones and say goodbye.
Thank you.
Goodbye.
Bye. Thank you.
You bet.